Hi. Section 2.4, one-sided limit. In earlier sections, we defined the limit. In definition, we say f has a limit around a when as x approaches a, the function values from both sides is approaching some value L. Now, in this section, we'll consider one-sided limit. So we'll try to see some details part by part, and eventually we'll try to expand the notion of limit for functions defined on general domain rather than only open interval. Let's see this definition. One-sided limit is the value the function fx approaches as x approaches a point and from one side only. So once if x approaches a from the right and the function value approaches L plus, then we say L plus is right-hand limit, and we can write in this way. So the limit of fx as x approaches a from the right equal L plus. Similarly, once x approaches from the left and the limit exists, then the limit is called the left-hand limit, and we write down in this way. So sometimes we call it limit from the left. Let's see this example. Earlier we solved this problem, and fx is given now x over x absolute value. Okay, that one. If x is positive, then x over x absolute value is same as x over x, which is 1. Now, once x is negative, then x over absolute value of x is same as x over minus x, so that will be minus 1. So the graph of the function is given here. So around 0, and once a value x is approaching to a from left-hand side and right-hand side, now left limit is minus 1, right limit is plus 1, so that the limit x approaches 0 of fx doesn't exist. However, now we can write the one-side limit in this way. In this case here, limit, okay, x approaches 0 from the left of fx, that is now minus 1. Now for this one, the limit x approaches 0 from the right, fx equal now 1. Okay, so we consider the limit part by part. And here, an earlier definition of limit requires the both side limit existence, and then now the same. So here, now fx has a limit as x approaches a if and only if the function has left-hand and right-hand limits there, and these two one-side limits are equal. So here, left-hand limit, right-hand limit should exist and the same. Then, in definition, the function has a limit as x approaches a, and the limit value is L. Okay, that is a definition, so that earlier definition for limit is only defined on open interval, so that around a, now left-hand side, right-hand side, the values are in the domain. If we consider one-side limit, then we don't have to define the function only on open interval. let's see this example. And for the function given in the graph, the domain is from 0 to, now the upper bound is 4. So the including 0 and 4, that is the domain. Okay. Here A, we are choosing A 0, 1, 2, 3, 4, and consider left limit and right limit and just the limit. Okay. Once x is approaching to A, 0, and from left hand side, but this is out of the domain, so that the limit doesn't exist. But x approaches A from the right, and is possible, and also we can see the limit is 1. So that in this case, now we can say that limit as x approaches 0, fx equal 1, because as that doesn't existence is now non-existent, is out of the domain. So the inside domain, we can say the limit exists. So around the end point, we define the limit along with only one-sided limit. Okay. Now, how about a equal 1? If you see here left limit, then it is 0. And if you consider right limit, then it's 1. So that is 0, and right limit is 1. So that eventually limit of f as x approaches 1 doesn't exist. That is now E existence and rotated and not, so that it means it doesn't exist. How about 2? And once x approaches 2 from left hand side, then the value is all the way 1. Now from right hand side is coming down to become 1, so that from both sides the limit is 1, so that we can say the limit exists, the same value 1. Now for 3, the same, left hand limit and right hand limit, both are 2, so that in 2 and 2, so that the limit is 2. Okay, how about the right end point? Here, left limit is as x approaches from the left to here now 4. Then the value becomes 1. So the left limit is 1, but right limit doesn't exist. However, this is outside the domain, so that for end point, just one side the limit exists, then we can say the limit exists. So the value is 1. Okay, now for one-side limits, we can define by using epsilon delta argument. And the right-hand limit, L, at point A can be written in this way, but with the epsilon delta argument, we can require in this way. Fx minus L in modulus is bounded by epsilon whenever A and x is in right side of x, but the epsilon, delta distance from A, and that is now A plus delta. Earlier, when we are measuring the regular limit, we consider the both side interval. Now for right interval, we require x is inside that half interval. So in this only right side, and whenever we are choosing x in this interval, then now this difference is bounded by epsilon. Then for any arbitrary epsilon, then we say L is the right-hand limit. Similarly, left-hand limit is now defined along with the condition that x is now the other half interval, delta interval from here a, and that is now a minus delta. So that once x is inside this half interval, and now the value is bounded by here difference bounded by L for arbitrary L, then we say L is the left-hand limit. Exactly the same way as for the regular limit, but we are considering for x now only one side. Okay. In this example, we'll prove that x approaches 0 from the right and square root of x equals 0. Okay. Now, so we have to, here for arbitrary epsilon, we have to find delta positive such that this equation is satisfied. So that is basically fx minus L absolute value is bounded by epsilon whenever x is now from 0 to 0 plus delta, which is right half interval. Okay. But it can be easily simplified in this way, and so that from this one, if you take a square, then x is bounded by epsilon squared, and so the requirement is that x is between 0 and delta. Whenever you choose x in this interval, then now x must be bounded by epsilon squared. So easily we can choose here delta equal epsilon squared or smaller than that, so that we complete the proof. Okay, now we'll try to find the limits involving sine theta over theta. And this one, now, okay, this is typo. Rather than x, it must be theta. Okay, I'll fix it. As theta approaches 0, sine theta over theta will be 1. Here we'll prove that. Now, by using the geometric interpretation for the angle, and we can see quite easily. And angle theta in radian is defined in this way. And along with the circle of radius 1, if the arc length is theta, then the corresponding angle is theta. That is a definition. So here, in this picture, now this is a circle of radius 1. Now this is case where theta is positive, and once it is hitting the arc, then for that point A, now this point is x component is cosine theta and y component is sine theta. So that means that geometrically this length is cosine theta, that is sine theta, and apparently this is longer than that one. So that is a theta. If this angle is theta, then this one in pink is basically the theta, so that, and theta is larger than sine theta, and tangent theta is now that one, so that it's now longer than that one. So we reach it over there. When theta is negative, that means if we consider the other direction, then we can reach at this one. Along with the negative, we can get it. But anyway, here, if we just divide the inequality along with the sine theta, in this case, sine theta is negative. In this case, sine theta is positive, so that from both of them, we reach at this inequality. And now, if we choose this reciprocal, then we can reach at that one. Now, here, and cosine theta is approaching 1 as theta approaches 0. So by using sandwich theorem, yes, upper bound is 1, lower bound is approaching 1, so that this midterm should approach 1. So we finish the proof here. Now, this one is quite useful, and we can solve many problems by using that. Okay, for this example, let's say part A. Now, the given problem, okay, once x approaches 0, then top and bottom simultaneously approaches 0. This one is the type of 0 over 0. Now, we'll manipulate a little bit. The given term is the same limit as x approaches 0. Now, top is sine 2x. Okay. Now, we have to put the same variable, so that 2x, so that we can use it. In this theorem, now that's theta and that's theta, so that this term, that term must be the same, and the theta approaches 0. So we have to put the same value. But once you change in this way, this term is not the same as this one, so that you have to scale it. Okay, for example, if you to put here 2 and 5, then this 2 and that 2 will be cancelled out, and bottom should be 5x, so that now, along with that scaling factor, this term is same as that. Okay, now here x approaches 0, and only we know from the previous theorem, and that the same, then x approaches 0 means 2x also approaches 0, so that this whole thing will approach 1, and this is constant. So eventually that will be 2 over 5. So that is the final answer. Now let's go to B. Okay. Now we'll try to use this equality, the half angle formula, so that cosine x minus 1 is the same as that one. So the given left side term is the same as, now there's a minus 2 sine squared x over 2 divided by x. So let's, okay, of course here we have a limit. We'll try to use the theorem. So we can write this one in this way, limit. Okay, let's put minus 2 separately. And then here we'll try to get here now sine x over 2 and another sine x over 2, and we have a bottom x. Okay, we'll rewrite here limit and minus 2, and that top one is sine x over 2, and here divide by same thing, x over 2. And with this one, we may try to put the remainder part, sine x x over 2, and now divide by 2 like that, so that this multiplication will make x, so the same as earlier one. Okay. Now by using the theorem, we know that once x approaches 0, then half x approaches 0, so that this term will approach 1. Now for this one, and sine x over 2, as x approaches 0, this top will approach 0, so that that one is now 0 over 2 shape, which means that is 0. Okay, earlier when we learned limit rule and this product rule, once each term has a limit, then we can apply the limit to each term and combine them for every multiplication, division, addition, subtraction, we could do that as far as the final form exists. So here, the limit can be applied, this term, that term, one is approaching 1, one is approaching 0, so that eventually the final limit must be 0. Okay. Now, by using this theorem, we can do this one. For example, limit x approaches 0 and tangent to x over x for this one. Now, that is the same as a limit. Tangent x is the same as now sine x divided by here cosine x and 1 over x. So we reorganize it. So that's a limit and sine x over x and 1 over cosine x. You can write in this way. Then x approaches 0. Then this one is approaching 1. Of course, here cosine x is approaching 1, so that is 1. So that is 1. So the final answer for this limit is 1. And now you can consider the reciprocal, and x over tangent x, also it will be the same. Because if you are taking the reciprocal, then once the limit is approaching 1, then its reciprocal should approach 1. It is a sort of a quotient rule, so that we can say that. So by using that, you can solve many limit problems. Now here, finally, we'll try to define sinc function. And we know that as x approaches 0, this quantity approaches 1. So that now when x equals 0, the value is 1, then now it fills that point, and this itself has no value at the 0, but along with this extension, we can fill out that portion. Particularly, after that, if we normalize, so that here, rather than x, we are using pi x, and also here the same pi x, then again, as x approaches 0, this whole value approaches 1 from both sides. And so we can define 1 at x equals 0. Then, again, same way. Now, for every integer value, sine pi times some integer value will be 0. So that you can see in the graph. So every integer except 0, now the value will be 0 and oscillatory, but oscillation becomes smaller, smaller, smaller. And that is normalized sinc function. It's quite popular, and later on we'll have some chances to use it. Okay, let's go to some exercise problems. Okay, for example, for this one, now it can be written, for example, tangent 2x divided by now 2x, and here 2 and 1, like that, right? So we already know that x approaches 0, then this the same thing, 2x and 2x, so that will approach 1, so that the answer will be 2. 1 times 2 equal 2. Now for this problem, and here you may consider for that problem, for example, theta equal 1 minus cosine t, then this term can be written now tangent to theta divided by theta. The same thing, 1 minus cosine t, 1 minus cosine t, and as t approaches 0, and here cosine t approaches 1, so that theta approaches 0, so that the problem can be written as limit theta approaches 0, tangent theta divided by theta. So the value is 1. Right? So for all of these problems using equation 2.25, which is that one here, this one, the limit of sine theta over theta as theta approaches 0 equal 1. Okay, now we'll go to one more problem. Okay, and once x is negative, then x squared sine 1 over x. Now once x is positive, then square root of x, and there's no value at x equals 0. Now we consider the left-hand limit of fx as x approaches 0, and now right-hand limit, and we try to get conclusion for limit of fx as x approaches 0. Okay, let's see the figure is x-axis, and then is y-axis. Now that value is oscillatory on the left-hand side. However, and because of x squared, the value is bounded by x squared, so that we have x squared, so oscillatory, and so that if we expand the symmetrically like that, the function value will be inside this one, so that oscillation, but the oscillation is becoming, magnitude is becoming smaller, so that now from this one we can see that the limit as x approaches from the left must be 0. Now how about the other side? Square root of x. Okay, square root of x is given in this way, and right side. Then of course here as x approaches 0, the limit, right hand limit is 0, so that here from left hand side, from right hand side, both have a limit and same value, so that here limit of fx as x approaches 0 must be 0. Of course it should exist, and the limit is 0. Okay, this is the end of the section. Thank you.